Hi there, my name is Declan Adams, and this is my submission for Lab 2 Projectile Motion. So to lay the foundation of this experiment, the purpose was to compare the change in position over time of a projectile in an observed scenario and a predicted computational scenario, one where there was just gravity and one where there was air resistance and gravity. And just for clarification, observed means a real-world experiment, and predicted is our glow script code. So to start, we need to talk about some fundamental physics principles, first starting with Newton's second law. This states that force is the product of mass times acceleration. Because we're using projectile motion, which concerns movement in the vertical direction and forces acting in the vertical direction, we want to look at the force of gravity. If we use this F equals ma, we know that the force of gravity is in the y direction, like we just said, mass, negative mass, times gravity. And we know that this is 9.8 because that is a constant. From Newton's second law, we can derive the position update and the velocity update formula, which tell us our final position and velocity after some period of time if we know our initial velocity and position. Another fundamental physics principle we know in this lab is air resistance, which is a type of friction that opposes the motion of an object in air. Here's the formula to calculate this, and our experiment works to determine what the value of B is computationally. If there's no air resistance, then F net, so the total forces added up, is simply equal to F gravity in this projectile motion problem. So, to briefly preview the results, did the projectile motion for the observed object match the computational model? No, and we'll discuss why in a second. Looking at our models, we have our system, which is this paper ball that's traveling in this video. In the surroundings is everything else acting upon it in the environment, so air resistance, gravity, etc. And so like I just said, the forces we have to account for are gravity, and in one of our computational models we have to account for air resistance. But we're assuming that we cannot calculate the applied force that threw the ball initially. So to look at our experiment, we first started by recording the paper ball moving in a projectile curve like you just saw, with no movement in the z direction but movement in the x and y. Then using Tracker, we found the ball's position frame by frame to determine the observed position, so the experimental part. Then using GrowScript, we created a computational model that predicts what the position should be with gravity only and with gravity and air resistance. Then we created a graph that we'll see in a second, overlaying the change in position over time for both the observed and predicted models. So the observed position was what I just said. We can see that it's moving in this video in a curve. Tracker generated this table with time, x position, y position, and this curve of it moving over time. And so looking a little bit closer at our experiment, we found that the total time to hit the ground was 0.733 seconds. The initial position was determined here, as you can see, from the table generated, and we found the change in velocity using the change in position over change in time formula. So here is the final position of x and final position of y, minus the initial position of x and y, which gives us this vector. So looking at our code, we determined that the mass of the paper was 0.005 kilograms. Here's our initial conditions that we just discussed. Delta T was calculated by taking 0.733 seconds, which was the total time divided by the number of frames, which was 22. G is 9.8, that's the gravity constant. V hat was defined for this drag equation. B was determined experimentally. Here's the force of the drag equation, which is just this computationally. And F net was the force of gravity plus F drag. But when we want to calculate just gravity, we take this component out. And here's our Newton's second law equations that we talked about in the very beginning. So with no air resistance, we see that the ball traveled into the negative y direction, whereas with air resistance, it stops at y equals 0. And so let's discuss these results. So overlaying them all together, we see that gravity only caused it to go way into the negative y direction, and was not correct. But we can see that when we had gravity and drag force, it was pretty close to the experimental finding of the position in the y direction and how long it took in seconds. Some sources of error include the x value in the initial conditions not truly starting at 0, and Tracker may have had some frame data errors because of the center of mass. So for the conceptual questions, do any of these models predict a terminal velocity? No. If there was terminal velocity here, we would expect to see a horizontal, because acceleration, which is the derivative of velocity, should be 0. Again, here we don't see any flatlining, which is how we know that there's no terminal velocity. But if we needed to determine an experiment to do that, we need a large surface area to a small mass and increase the height. And if we were to throw the object straight up, then the object thrown straight up would take more time because it would need to go up, then all the way back down, whereas ours just went like this, so there was none of that initial time of going straight up. And we know that and prove that mathematically with the kinematics formula shown here. Thank you.